That happened last time, but I'll have an audio, probably audio and video that I can send you guys whenever I get one of these two nice people recorded, and so we're good. So I should be recording now. I've got my old system in place, and so I have to walk around with this, but that's okay. I've looked silly before. At least I'm not taking pictures with it. You see people taking pictures with my iPad? It's weird. No judgment, a little bit of judgment. So you had some reading today, and you also had a couple of short little videos from me, some questions. Remember that? How did that go? I haven't looked at your results yet. Those are not, the Sakai thing is not graded, but I can see how you did generally. So the first thing that we're going to talk about today is the resting membrane potential. Okay, and this is a concept that's very similar to what we covered in that Sakai reading, and that concept dealt with the equilibrium potential, right? So there's resting membrane potential, which we can define as the measurement of the separation of charge at the cell membrane. Okay, it's measured in volts, right? Volts are or millivolts, a measurement of force, right? The separation of charge, and it's, in theory, has the ability to do work, right? And it's a force. Okay, so we can measure that, and the resting membrane potential is the result of accumulation of lots of different things happening. Okay, equilibrium potential is a little bit more specific and is a component of resting membrane potential. So, first things first, based on what you understood, can someone help me define the equilibrium potential for the class? What is an equilibrium potential? Brave soul. Yes?
A voltage where an ion doesn't have a net movement.
Okay, we have a voltage, there's an ion that does not have any net movement across the membrane anymore, right? So it's a charge, an ion that could pass through the cell membrane, right? And has passed through the cell membrane, but is no longer experiencing any net movement. Okay, right? And it's a balance of two forces, right? It's a balance of two forces on that ion. What are the two forces? Yeah. Right, so the concentration gradient, what we talked about last time was that we have diffusion gradients for different chemicals, right, across the membrane. And if we take potassium, for example, there's a diffusion gradient pushing potassium which way? Out of the cell or into the cell? Out of the cell. It's high inside, low outside. So there's a diffusion gradient that in some has the result of pushing potassium out. What's the balancing force? What's the opposite force that develops?
Electrical force?
Yeah, there's an electrical force, right? So positives attract, positives attract negatives, negatives attract positives, right? But negatives and negatives repel, and positives repel, right? You know that, I have to teach that. So when we have positive ions moving across the cell membrane, right, accumulating, there's going to be an electrical force of positive charges repelling one another, right? And pushing those positive potassium ions back across the membrane. Okay? So an equilibrium potential is a balance of those two forces for a particular ion. Okay, we're talking about one type of ion. Example is potassium, there could be anything. And the equilibrium potential is where, or at what voltage, at what measurement, does that ion reach equilibrium between its chemical diffusion forces and its electrical forces. Okay. All right. So if we're gonna, if we can, maybe we can make that simpler, right? A little bit shorter. Defining an equilibrium potential. This is the voltage at which an ion, comma, permeable to the membrane, comma, reaches an equilibrium between its chemical and electrical forces. Okay. So we could look up in Wikipedia maybe, or at least something, some database somewhere, and look up what is the equilibrium for potassium. Okay. That number in the body is a relative constant. Okay. But we'll see that it's not. It can change a little bit. Okay. It can change. But if we measured all of our potassium levels, they'd be pretty much the same, comparing inside to outside. Okay. And we can say that because of this, we've got a pretty stable equilibrium potential. Okay. So if we think about an equilibrium potential in that context, in which it was described, in which you read and which you watched, what is one factor, or the major factor, that the equilibrium potential of potassium is going to be dependent on? What is the one factor that will have the biggest effect on this? Yeah. Concentration gradient of potassium. Okay. Now, sodium, nothing to do with sodium, nothing to do with chloride, nothing to do with glucose, nothing. Okay. Only potassium. Okay. So you can kind of imagine this principle of an equilibrium potential as applying to a cell with one type of leak channel that allows one type of ion through. Okay, so in this case, let's talk about potassium because this is pretty close to what we have in our cells. Okay, we've got potassium leak channels. Potassium is high inside. All right, so we can say lots of potassium inside. Right? Really tiny little potassium outside, low concentration potassium inside. Outside. High inside, low outside. Okay. So if we have this really big concentration gradient between the two sides of the membrane, we're going to have a high equilibrium potential. That is where the membrane potassium reaches an equilibrium is going to be at a strong voltage. Okay. Far from zero. Okay. But if there's a very weak difference between inside and outside, you're going to only have a weak equilibrium potential. Okay, so where it finds its equilibrium depends upon initially that strong chemical diffusion force. Okay? All right, anybody know what the typical value of potassium is? Equilibrium potential of potassium?
-90.
Yeah, -90. Commit that to your heads somewhere in your brains. Okay? Minus 90 millivolts is the typical value, okay, and that's based on typical values of intracellular potassium and extracellular potassium. So, what could make this equilibrium potential stronger, though? Okay, and by stronger, I mean further from zero, in whichever direction we're talking about. How could you make an extracellular change in the potassium concentration to make this stronger? Yeah.
Have less potassium outside the cell, so the concentration gradient pushes it out more.
Right, so if we have less potassium out of the cell, we'll have a bigger gradient. Right. So let's say we could bring that down even further. Instead of 4 or 5 millimolar, we could have 3. Okay. That would give us an even stronger potential, which would be more negative. Okay. What about an intracellular change? If we could somehow make that bigger, right? So if you make the big bigger, the small smaller, right, we get a stronger gradient, okay? So is that possible in our body? Is it possible we might have fluctuations in our extracellular potassium? Yeah, right? Bananas, whatever you eat, that's made of cells gives you potassium, right? Because cells contain not only human cells, plant cells, animal cells, they all contain potassium. Okay. So you eat vegetables, they're packed full of potassium. Okay. That's good. But if you eat too much too quickly, and you can't, probably, there's other ways this can happen. But in theory, you could ingest lots and lots of bananas, right? You might elevate your potassium outside, and that would make your gradient smaller. Okay, and you might get closer to zero. Okay, so this equilibrium potential depends upon the concentration gradient, right? And if you remember from our calculations in that online unit, it has to do with that calculation we called the Nernst equation, right? This is the point where you might want to leave. Nernst equation, remember the Nernst? So the Nernst equation is a way to calculate that equilibrium potential. Okay. All right, so most cells, however, they are not made up of one type of leak channel for one ion. Okay? They are made up of a combination of things. Okay? So let's just add one other component, right? We've got potassium leak channels, and let's say we have, in addition to that, we have sodium leak channels. Okay? And we could calculate that we've got an equilibrium potential for potassium of minus 90 millivolts. Right? Potassium tries to leave the cell, and as it does so, build up a negative charge inside of the cell, right? And that negative charge is why we say it's a minus 90. Okay? If it were sodium, if we had nothing but sodium channels, we would have a equilibrium potential for sodium of about plus 60. Okay? Sodium, highly concentrated outside, would push its way into the cell, right? Bring those positive ions to the inside. Now the inside is becoming positive. Okay? So its equilibrium potential, based on its concentrations, is usually about plus 60. Okay, so what if we have a cell, and we do have cells that have both types of leak channels. Okay, so we have permeability to both types of ions. Where is the membrane potential going to be? Potassium, think about it in, this is a little bit anthropomorphizing, but potassium is quote unquote trying to move out of the cell, right? Because it's got this diffusion gradient pushing it out. And it's not going to be happy until it has reached that equilibrium, right? And sodium's doing the opposite, it's pushing its way in, right? And the concentration gradient is pushing it in until it develops enough of a positive interior. So what's going to happen? Who wins? Yeah. Well, potassium does win, right? but how do we know? Yeah, it's the one that's more permeable. Okay, so it's like there's a race between these two ions trying to go through the channels to get to their equilibrium potential. Okay. Remember, an equilibrium potential is a value for an individual type of ion. So each sodium has its own, potassium has its own. Okay, so if we have lots and lots of permeability to sodium and very little to potassium, our potential is going to be skewed towards sodium's equilibrium potential. Okay? But if, on the other hand, we have, like we do in most of our cells, we have far more potassium channels. Right? Now the membrane potential is going to get a lot closer to what potassium is. Okay? So you may have learned in 252, a typical resting membrane potential of a neuron is about minus 70, right? And that comes from primarily permeability of potassium, attempting to reach its equilibrium potential. Okay? But there's a little bit of permeability. It turns out something like 97%, 96% permeability to potassium, and like 3 or 4% permeability to sodium. Okay, so it's really, really skewed. Okay? So what's happening then in a cell membrane like this is that we've got ions moving through the cell membrane, right? There's a constant efflux of potassium, right? Because potassium is never going to get to minus 70, right? So there's a constant loss of potassium and a constant gain of sodium, okay? And they, at some point, reach their own balance, right? They reach their own balance. That's somewhere between minus 90 and plus 60, okay? And where that is, it's not the halfway point, unless it's 50-50 permeability, okay? Where that in-between value is, where we have these two things happening in opposition to one another, is much closer to the potassium side, because there's much more permeability to potassium, okay? So, what if we have more channels? Yes. Who wants more channels? Okay, you guys are too spread out here. If you get all together like you do for a basketball game, everything's much more exciting. So don't sit in the last, was it 12 rows? Okay, don't count. So let's say we've got chloride too. And we do, we have some chloride channels, okay? So, and we can have permeability to other things too. So what we do here is we have this equation at the top. No, you will never be asked to solve this equation. You're welcome. What is this one called? NERS. And this is how we determine an equilibrium potential. Okay? Equilibrium potential is the potential for one ion, where that one ion would land as a balance of its chemical and electrical forces if we only had channels for that one thing. Okay? But the moment we start adding other types of channels, now we have to, if we want to calculate where that equilibrium is going to be, we have to think about, okay, well, who's got more permeability, right? Is it going to be closer to this or closer to that? Okay? And so this equation at the bottom, which you also do not have to solve, you're welcome. This is the Goldman's equation. And this is useful for determining the resting membrane potential when you have more than one ion. Okay? Here it's the E sub m, okay, voltage of the membrane. Okay. So if we take a look at this, math geniuses out there, what are we doing essentially? What is this P K? What is this P Na? What is this P chloride? These are the relative permeabilities. Okay, so potassium is 80% and chloride is another 17%, and sodium is, what's the last three? Okay, this is basically just taking the total permeability to ions and saying in what proportion is it permeable, okay? And so the idea behind this equation is it's just extending the NERDs to account for multiple ions, okay? And when we do this, we come up with a value, all right? And so if you plug these values in with the right concentrations inside and outside, you'll end up with something like -70 for a typical cell, okay? Thursday, we're going to talk about cardiocytes, okay? And if we have, in the case of cardiocytes, they have a resting membrane potential of -90. What does that tell you? What if you see a cell that's got a resting membrane potential of -90? What does it probably not have? It probably doesn't have sodium channels, right? Or not sodium leak channels. That's what we're talking about. Yeah. But if we're talking about a neuron with a resting membrane potential of -70 or -80, there's a little bit of permeability. Okay.
Where did the 61 come from? Like, how did they figure out?
Where?
And
I don't see
equation.
61 log.
Oh, the 61 is the combination of those constants. I just simplified. We don't need to worry about temperature or that other garbage. Okay, so when it comes to the resting membrane potential, we've got a variety of leak channels that help refine the membrane potential, resting membrane potential. Okay. All the while, if you've got permeability of 3 different ions, every one of those ions is moving through the channels in an effort, if we're going to be anthropomorphizing here, but in an effort to reach its own equilibrium potential. Okay? So potassium's starting to get to -90, chloride happens to be about -90, sodium's trying to get up to +60. Okay, so that's the typical set of ions we're dealing with. Most of the time we kind of ignore chloride because it has the same resting membrane potential as potassium, and it's not nearly as permeable. Okay, so there's one other thing here. Sodium potassium pump. Remember this thing? All right, so if you open any introductory anatomy and physiology book, we're gonna be talking about this pump. And they very often explain this thing as responsible for the membrane potential. Okay? I just told you how membrane potential is formed, right? It has nothing to do with this thing, right? So in what way does this pump contribute to the membrane potential? Yeah. He said it a little louder, it's perfect. It maintains the concentrations of potassium, as the potassium being high inside of the cell, right? And sodium being high outside of the cell. Right? So if it wasn't for this channel, as we talked about last time, we wouldn't have any difference in sodium and potassium across the cell membrane, right? So in the sense that this is the thing that gives us the concentration gradients to begin with, right, that allow us to fill in our equation here at the bottom with the sodium concentration and the potassium concentration. In the sense that this thing gives us those concentrations, it is responsible for the resting membrane potential, okay? But it has nothing to do with the fact that it's moving ions 2 to 3. Okay? Kind of. Okay, so the one caveat to this is that if you're moving 3 positives in one direction, 2 in the other, yes, you're making a small charge. Okay, but it contributes to the entire resting membrane potential of minus 70. It contributes something like minus 2 or 3 millivolts. Okay, the direct action of this pump working has very little direct effect on the membrane potential, but it is responsible, and not just this cell that we're thinking about, but every cell in the body's got one of these pumps, right? So every cell in the body's got lots and lots of sodium potassium pumps and is responsible for making sodium high outside and low inside of cells. Okay. Any questions about that? Okay. Let's pull everywhere. Activate. Okay. So let's just do a quick check on this basic concept. There we go. Okay. All right, so I want to tell you a secret to answering questions. If you read a question that is not a simple recall, draw yourself a little picture, right? So we got a cell, we got sodium high on the outside, right, and low on the inside. You know that, right? Right, which you know in school. Okay. So what would we need to do to lower the equilibrium potential? What do we need to do to those concentrations? Do we need to make that difference bigger or smaller? Okay, so we need to smallify the effect, right? Make it smaller. And we can do that in different ways, right? We could make the outside less concentrated, the inside more concentrated. Okay. All right. Anybody want to change their answer yet? Raise your hand if you're thinking about it. Yeah? Okay, good. All right. Let's talk about sodium potassium pump. Sodium is pumped out, right? Potassium is pumped in. Okay. So what does this pump do for the sodium equilibrium potential? Does it help to maintain it and keep it strong? Or does it diminish the gradient between the cells, the inside and the outside? It helps maintain it, right? So its job is to make the outside as sodium rich as possible, right? And the inside as sodium poor as possible. Okay? So that pump is helping us, right? Anybody want to change their answer yet? Okay. Shall I let you? Let's see what you, okay. There's more to this, but let's see where we're at.
Did the check mark the correct number?
I already showed the correct, didn't I? So somebody, take this a little bit further now that I've given you the right answer and leading up to it. Almost. Why? So first off, you have to remember what digitalis does, right? What does digitalis do?
Strengthens contraction of the
Yeah, it messes up the sodium potassium ATPase. Okay? So if we have a pump whose job is to make the sodium gradient strong, and we interfere with its activity, right, what's going to happen with sodium gradient? The concentration gradient is going to decrease, it's going to be less strong. Okay? And therefore, we've diminished the equilibrium potential for sodium. Okay. That makes sense? How many of you, to be honest, did not remember what digitalis? Okay, that explains it. All right, good. So sometimes hard questions are not hard conceptually, but you got to know the pieces. Right? This is an example of a hard test question. Okay. And it's hard because, yes, you have to sort of understand concepts, but you also have to have the vocabulary of pieces that we've learned along the way. Okay, so any question? Yeah.
Why is like messing with the permeability wrong?
Why is messing with the permeability wrong?
Why is the
Oh, okay. You're referring to those questions. Morally? Yeah. Okay, so if you affect the permeability, okay, the only thing that you are affecting is the ability of sodium to move across the membrane. Okay? An equilibrium potential has nothing to do with permeability except that there has to be some permeability. Okay? So if you have more permeability, that just means you can reach your equilibrium potential faster. Okay? So the equilibrium is, remember there's a balance of chemical and electrical forces. Okay? So wherever they balance, doesn't matter if you make the door wider or close the door a little bit. Okay? It only has to do with, can they get through? Yes or no? And if they can, then what matters is the concentration gradient that's going to push enough ions out to make an electrical reflection. Okay? Yeah, so the permeability doesn't matter here. Okay? Now, that said, if you have a cell with sodium and potassium permeability, and you increase the permeability of one of those channels, you're going to affect where the membrane potential lands. Okay? But you haven't affected the equilibrium potentials where those ions are trying to get to. Okay. Sometimes I feel bad for you to let you get a free point like that. So, all right. Okay, so an extension of what we've been talking about is this concept. One more concept here, and then we'll move on to a totally different topic. of an electrochemical driving force. Okay? So, if we have a cell with some permeable channels and ions moving around, okay? And if we want to think about where the status of that ion's movement is with regard to its chemical forces and electrical forces, that's where this idea about the driving force comes in. Okay? So it's essentially acknowledging that there are diffusional forces, chemical forces that move ions, and there are electrical forces that move ions. Okay? Okay? So this is something that's very relevant to understanding why ions will move through channels. And we've already talked about how ions are moving through leaf channels because of electrical and chemical forces. But what happens, to illustrate this principle, what happens when we have a resting membrane potential? Okay? We have a resting membrane potential established by leaf channels, mostly potassium, a little bit of sodium. And we have another type of channel here, okay? We have another channel that is permeable to sodium, but it's not always permeable to sodium. Okay, this is what we might call a gated channel, that it can open, but most of the time it's closed. Okay? So knowing that we have an equilibrium potential of plus 60 for sodium, we know that when we open this channel, sodium will try to move through the cell membrane until it gets to plus 60. Okay? So if we've got a cardiocyte, minus 90 millivolts, and this is what we'll see Thursday. We've got a cardiocyte, heart muscle cell, minus 90 millivolts. It contains voltage gated sodium channels. When they open, sodium is permitted to move through the cell membrane. Okay, remember, we've got a resting membrane potential at minus 90. Okay? And we have an equilibrium potential for sodium that is very, very different. Okay? So this concept of electrochemical driving force is essentially, if we want to think of it in mathematical terms, it is the difference between the equilibrium potential, in this case it's sodium, okay? The difference between that and the resting membrane potential. Okay? It's the difference. So conceptually, what I'm talking about here is we're going to open a sodium channel, and we want to know what's going to happen to the sodium. It's going to move in, obviously, right? But why is it moving? There are both, and here's sort of the crux of this. There are both electrical forces pushing sodium in, right? Because it's positive ion and it's negative inside. There are electrical forces pushing sodium. And there are also chemical diffusion forces pushing it. So we can combine those two and say that the electrochemical driving force is the mathematical difference between the equilibrium potential and where the membrane potential currently is, the resting membrane potential. Okay? So what is that value if we just calculate it? Plus 60 minus negative 90, what's the difference? This is hard, isn't it? What is the difference? 150, okay? 150 millivolts. What that tells you is that this is the strength at which sodium will pour into the cell. Okay? So sodium will move into the cell with a lot of force. Okay? If we had an electrochemical driving force of 3, you're going to get a very small, weak movement of ions. Right? So the stronger this electrochemical driving force, the more forcefully those ions are pushed in. Okay? It's a mathematical way of looking at both the chemical and electrical forces together, describing where the ions are going to move in with what force. Does that make sense? Okay, so electrochemical driving force is just the difference between these two values that we've been talking about. Okay. And this only is relevant if we have a channel that we can suddenly open and drive some ions into or out of the cell. All right, questions on this? So when we get to cardiocytes tomorrow, we'll talk about this, and we'll talk about how when we open up one of these channels, the reason that cells are going to be flooded with sodium is because of that electrochemical driving force. Okay? Or in other words, the equilibrium potential for sodium is so far away from the resting memory potential that ions are moving very forcefully. Yeah.
Does it matter if it's like a voltage gated channel versus a leak channel?
Now, we could be talking, well, in a leak channel, there's not going to be with a leak channel, there's not going to be an electrochemical driving force. Right? Because those ions are always permeant to the membrane, right? I mean, you can talk about it, right? You can discuss the fact that, if you've got a minus 70 membrane potential, your potassium has an electrochemical driving force of 20, right? That's offset by sodium. But mostly when we encounter this term, it's going to deal with ions moving across cell membranes in a gated fashion. So it could be voltage gated channel, it could be lighting gated channel, it could be mechanically gated channel, right? Lots of different things that could make that change. Is there another question in the back? Okay. Any other questions about that? How do you have a good sense of how the membrane potential is made up now? It's all these ions fighting to get to their equilibrium potentials, essentially. Okay. And the ones that are the most permeable have the most to say about where that value is going to reside. Okay, so with the time left, we're going to talk about this one other topic. So we've been, the theme for today and previous class has been membranes. Okay? And I want to talk a little bit about osmosis. This is an incredibly important thing when it comes to how lots of parts of the body function. So I want to cover some things here with osmosis. First, let's define some terms. What is a mole? You took chemistry, you know the answer to this. Somewhere in your brain. Yes? Avogadro's number of molecules. Okay. So, let's put this in biologist terms. Right? It's a measurement of the number of molecules. Okay? A mole has a specific number, right? Is it 6.02 times 10 to the 23rd? Whatever. Okay. But it's a number. It's a number of molecules. What is an osmole? We're talking about osmolarity, right? What is an osmole relative to a mole? If a mole is any measurement of particle number, what is an osmole? You've never heard this term? Probably not. Yeah.
Just the water molecules.
No, it's not quite the water molecule, but it's the effect of those molecules on water. Okay. So,